Chapter 12, Elementary Chemical Kinetics. Section 12.7, Reversible Reactions and Chemical Equilibrium. Reversible reactions are not elementary because they involve two steps, forward and reverse. When both the forward and reverse reaction steps are elementary, we can write out this mechanism with two reaction steps from A to B and from B to A separately. From A to B, we have a rate constant denoted by K sub A. From B to A, we have another reaction rate constant denoted by K sub B. Now let's look at dA over dt. It's equal to KBB minus KA because A is consumed in the forward step. A is produced in the backward or reverse step. Therefore, we have two terms here, and from A to B, the reaction rate is KAA, and that's why you have that here. There's a negative sign in front because in this step, A is consumed. In the second step, A is produced. Therefore, we have positive KBP, KB times B, where KB times the concentration of B is the reaction rate for this reverse step. What about dB over dt? Well, B is consumed in the second step with KBB as the reaction rate, and B is produced in the first step with a rate of KAA. Therefore, dB over dt is KAA minus KBB. If you add up these two equations, you're going to see dA over dt plus dB over dt is equal to 0. These two cancel, these two cancel. That means A plus B remains constant. Why is that? Well, it's just because when A is consumed, you produce the same amount of B. If B is consumed, you generate the same amount of A. So the sum of A and B never changes. Now, for simplicity, let's assume the reaction system does not contain B initially. That means at time 0, B naught is 0. And therefore, A plus B is always equal to just A naught. B is just A naught minus A. Well, what if there's B at the beginning? Well, then B is A naught plus B naught minus A. Alright, but that's just slightly less convenient. Now let's assume B naught is 0. Then we have this equation. dA over dt is KBB minus KA. And the concentration of B is A naught minus A. So we plug that in. And then we need to solve this equation. How? Well, first separate the variables. We have dA over this entire equation of A equals dt. Then we integrate both sides. The derivation is non-trivial, but if you are good at integral calculus, you will get to this. A is A naught times a fraction. On the bottom, we have Ka plus Kb. On the top, we have Kb plus the product of Ka and exponential function. The exponential function is e to the power of negative K plus Kb multiplied by time. So we have that equation for A here. A is just A naught times a fraction with K plus Kb on the bottom, with Kb plus a product of Ka and an exponential function on top. E to the power of negative Ka plus Kb times multiplied by time. What about B? B is A naught minus A. So we just use A naught minus this expression, and we'll get just Ka minus Ka times the same exponential function on top, K plus Kb on the bottom, and then multiply by A naught. We can verify these two equations at time 0 and time infinity. Time 0 is very simple. You just plug in t equals 0 here, and on top you have Kb plus Ka. On the bottom you have Ka plus Kb. Therefore, A is just A naught. What about B? Well, B is A naught minus A. Alright, when A is A naught at time 0, then B is just 0. So we can verify these two equations at time 0 easily. At time equals infinity, well, same thing. We just plug in time equals infinity here, and this exponential function becomes 0, and this one also becomes 0. And therefore, we have also two expressions for A and B. A is KB over Ka plus KB times A naught. B is Ka times, divided by Ka plus KB, and then times A naught. Now look at this. If you sum them up, of course you get A naught, because on top you'll get KB plus Ka. On the bottom you have Ka plus KB. So A plus B is equal to A naught. That's good. Now let's look at B over A. When time is equal to infinity, what is B over A? Well, that's just the equilibrium constant, right? The concentration of the product divided by the concentration of the reactant at equilibrium. We're assuming when the time approaches infinity, the reaction approaches its chemical equilibrium. Alright, so we have B over A is the equilibrium constant for this reaction. And also, if you use these two equations, B over A is Ka over Kb. A naught cancel, Ka plus Kb cancel, and again, B over A is just Ka over Kb. And that also makes sense, because when you look at this equation, that tells you Ka times A equals Kb times B. Ka times A is the forward reaction rate. Kb times B is the reverse reaction rate. And we know at equilibrium, well, the forward and reverse reaction rates are the same at equilibrium. So everything makes sense here. Again, the equilibrium constant is the forward reaction rate constant over the reverse reaction rate constant. You might have learned this in general chemistry. Now let's look at one numerical example problem, 12.7.1. In a reversible reaction mechanism, we have two elementary steps, from A to B and from B to A. Let's say the initial concentrations of A and B are 0.3 molar and 0.1 molar. So we're making it more general. We allow B to exist at the beginning, and the Ka and Kb are 0.009 per second and 0.001 per second. Now let's calculate the concentrations of A and B. When the reaction reaches equilibrium, at equilibrium we have the forward reaction rate equal the reverse reaction rate. So Ka is equal to Kbb. And then we have 0.009 times A equals 0.01 times B. Therefore, B should be 9 times the concentration of A at equilibrium. Again, I have this equation because at equilibrium, the forward and reverse reaction rates are equal. And then we get this conclusion, B is equal to 9 times A. At equilibrium, we have B plus A is equal to 0.1 plus 0.3. So that's 0.4. Why is that? The sum of B and A never changes. So we have this 0.4. Now we have two simple equations. B is equal to 9 times A at equilibrium. B plus A is 0.4 at equilibrium. So how do we solve this? Very simple. Two linear equations, two variables. Just solve them. You get the final concentrations of A and B at equilibrium. For A, it's 0.04. For B, it's 0.36. We can easily verify these two numbers. This B concentration is 9 times A, and the sum is 0.4.